Saturn looks peaceful from a distance. That's the whole problem. From Earth, it sits in the night sky like something someone placed there on purpose, ringed, golden, almost decorative. Astronomers named it after a god of harvest and abundance. Artists painted it. Children point to it in science textbooks. For centuries, it carried the quiet reputation of the solar system's most elegant world. And then we actually went there. Not just a telescope pointed at the sky, but actual machines, probes built from aluminum and plutonium, launched across billions of miles, arriving after years of silence. What they found didn't match the postcard, not even close. Before this video is over, we'll come back to the single number that one scientist called the most unsettling measurement in planetary science, and we'll explain exactly why Saturn earned the word dangerous in a way no other planet in our solar system has. The story doesn't start with danger. It starts with beauty, which is almost always how these things start. For most of human history, Saturn was just a light in the sky. Ancient civilizations tracked it with the naked eye, gave it names, built myths around its slow movement. It was the farthest planet visible without a telescope, which gave it an air of mystery, distant, unknowable, sacred. Then, in 1610, Galileo Galilei turned a crude telescope towards Saturn and saw something strange. The planet appeared to have ears. He didn't know what they were. He wrote that Saturn appeared to be a triple body, 3 spheres pressed together. His instrument wasn't sharp enough to resolve the rings as rings. It took another 50 years. In 1659, the Dutch astronomer Christian Huygens looked through a better telescope and finally understood what he was seeing. A ring. A flat, thin ring surrounding the planet, tilted at an angle. He published the finding cautiously, aware that no one would believe him immediately. He was right to be cautious. The ring changed everything about how people saw Saturn. It made the planet more beautiful, not more threatening. Observers spent the next 2 centuries mapping ring features, naming gaps, cataloging bands. Giovanni Cassini found the most prominent gap in 1675. They called it the Cassini division. The whole enterprise felt like art appreciation. That framing lasted for 300 years. You'd think something that elegant couldn't be hiding anything. It can. Let's build the picture layer by layer, starting with raw scale, because the numbers matter and they don't behave the way you expect them to. Saturn is the second largest planet in the solar system. Its diameter is roughly 9.5 times the diameter of Earth. If Saturn were hollow, you could fit more than 700 Earths inside it. That's not a metaphor. That's the math. But here's the thing that catches most people off guard. With all that size, Saturn is the least dense planet in the solar system. It's less dense than water. If you could find an ocean large enough, Saturn would float. That sounds almost comic. A planet the size of 700 Earths floating like a bath toy. It isn't comic once you understand what that density tells you about what's inside. Saturn is composed almost entirely of hydrogen and helium. Not rock, not metal, gas, compressed into exotic states by gravity so powerful it bends the rules of familiar chemistry. Near the core, pressures become so extreme that hydrogen stops behaving like a gas and starts behaving like a liquid metal. It conducts electricity. It flows. It generates a magnetic field. That magnetic field is what you need to remember. The winds on Saturn run east to west and west to east in alternating bands called jet streams. These aren't gentle breezes. The fastest measured winds on Saturn move at roughly 1,800 kilometers per hour. To put that number in terms your body understands, the fastest wind speed ever measured in a tornado on Earth was a little over 500 kilometers per hour. Saturn's winds are more than 3 times faster than the worst tornado ever recorded. And those winds never stop. There's no friction from land. There's no ocean surface to scrub energy away. There's no seasonal pattern that causes them to decay. Saturn's jet streams have been running continuously for as long as we've had instruments capable of measuring them, and almost certainly for billions of years before that. Here's the escalator. You'd think the wind speed would be the worst of it. It isn't. Saturn's atmosphere is also full of lightning. Not occasional lightning. Persistent, continent-scale storm systems that discharge lightning bolts roughly 10,000 times more powerful than a typical bolt on Earth. The Cassini spacecraft detected radio bursts from these storms, signals so strong they were initially mistaken for something else. Scientists had to recalibrate. There's a storm system at Saturn's North Pole that nobody fully understands. It's called the hexagon. It's a persistent, 6-sided atmospheric pattern the width of 2 Earths. It was first observed in 1981 by the Voyager probes. It was still there when Cassini arrived decades later. It's still there now. A hexagon, on a planet, rotating with the storm, stable enough to photograph cleanly from billions of miles away. The physics of why a hexagon forms rather than a circle are understood in rough terms. It involves wave interference patterns in the jet stream. But why it's so stable, why it hasn't broken apart, why it maintains that geometry across timescales that would shred any weather system on Earth, those questions don't have clean answers. Now we reach the moment the picture cracked open. In 2004, after a 7-year journey across nearly 1.5 billion kilometers, the Cassini-Huygens spacecraft entered orbit around Saturn. It was the most ambitious planetary mission ever launched at that point, a joint project between NASA, the European Space Agency, and the Italian Space Agency. The spacecraft weighed nearly 6,000 kilograms at launch. It carried 12 separate science instruments. It would spend 13 years in Saturn's system. What Cassini found over those 13 years rewrote the threat profile of the Saturnian system completely. Start with the rings. From Earth, the rings look like a continuous solid disk. They aren't. The rings are composed of billions of individual pieces, ice, rock, and dust, ranging from the size of a grain of sand to the size of a house. The total mass of the rings is roughly equivalent to the mass of the moon Mimas, one of Saturn's smaller moons. And the rings are actively unstable. Cassini measured a process called ring rain, a continuous flow of ring material falling into Saturn's upper atmosphere at a rate roughly equivalent to emptying an Olympic swimming pool every 30 minutes. The rings aren't permanent, they're disappearing. Slowly on a geological timescale, but disappearing. Current estimates suggest the rings could be gone within 100 million years. That sounds like a long time. On cosmic timescales, it's nothing. And here's the part that compounds the unsettling quality of that estimate. The rings themselves may only be a few 100 million years old, which means we might be living in the brief window of time when Saturn has rings at all. That's one of the quietest revelations in modern planetary science. We didn't just discover Saturn's rings, we discovered that we caught them at a moment in their existence. Like walking into a burning building just after the fire started. Another civilization 200 million years from now won't see them. Another civilization that existed 200 million years ago wouldn't have seen them either. The timing is, statistically speaking, extraordinary. But the rings are not the most dangerous feature of the Saturnian system. The most dangerous feature doesn't orbit at the planet. It hides inside a moon. Enceladus is small. It's only about 500 kilometers across, roughly the size of the state of Arizona. It's covered in bright white ice. From a distance, it looks inert, geologically dead, safe. In 2005, Cassini flew close to Enceladus and measured something that was not supposed to be there. Heat. Specifically, a warm region near the South Pole. And then, plumes. Enormous jets of water vapor and ice particles erupting from cracks in the surface called tiger stripes. Parallel fractures running along the southern hemisphere, each roughly 130 kilometers long. The plumes were shooting material into space at speeds sufficient to escape Enceladus entirely and feed Saturn's outermost diffuse ring, the E-ring. Under that ice, Enceladus has a global subsurface ocean. Not a small pocket of water, a global ocean, in contact with a rocky sea floor, kept liquid by tidal heating as Enceladus is flexed by Saturn's gravity. Cassini flew through those plumes and tasted them. The instruments detected water, salts, silica nanoparticles, carbon dioxide, and organic compounds. Organic compounds on a moon of Saturn. The silica nanoparticles were particularly significant. The specific size of those particles tells you something about the temperature of the water that formed them. They form only in water that's at least 90 degrees Celsius, hot hydrothermal water, actively reacting with the rocky sea floor. In other words, Enceladus almost certainly has active hydrothermal vents on its ocean floor. On Earth, hydrothermal vents are where life first appeared, according to leading theories. They are chemical engines that produce energy from the reaction between hot rock and cold seawater. Every ingredient for that process appears to be present inside Enceladus, a moon that looks completely dead from the outside. That's the revelation that arrives at around 35% of what we know about Saturn, and it changes every prior assumption. Saturn isn't just a pretty ringed gas giant. Its gravitational reach is actively squeezing a small ice moon, generating enough heat to maintain a liquid ocean for potentially billions of years, pumping organic material into space continuously. The question isn't whether Enceladus could support life. The question is whether it already does. Now come back to your own body for a moment. Think about the room you're in, the floor under you, the atmosphere pressing down on you from above. Every physical structure around you exists because of a relatively narrow set of conditions: temperature, pressure, chemistry. Change any of those conditions sharply, and the structure fails. Now imagine you're falling through Saturn's upper atmosphere. You'd enter a layer of ammonia ice clouds, the visible surface, the golden bands you see in photographs. Temperature at this level runs around negative 140 degrees Celsius. Below that, a layer of ammonium hydrosulfide clouds, darker and more chemically reactive. Then a layer of water ice clouds. And all around you, those winds, 1,800 kilometers per hour lateral velocity, not gusting, constant, every second, the pressure mounting as you fall deeper. By the time you've descended roughly 1,000 kilometers, the atmospheric pressure would be several hundred times what you experience standing on Earth's surface. the temperature would have climbed past the boiling point of water. The hydrogen around you, compressed to densities you've never experienced, would stop behaving like a gas. There's no surface to land on, no bottom to reach. The planet just gets denser and hotter and more extreme until, far enough in, it becomes something no human instrument has ever directly measured. That's not a metaphor for mystery. It's a literal statement. We don't have a probe that survived a deep Saturn dive. The pressures involved would destroy anything we've built. And this is where a second layer of danger reveals itself, one that isn't physical, but mathematical. Saturn's gravitational reach is extraordinary. The planet has 83 known moons, 83 distinct objects caught in its gravity, ranging from Titan, which is larger than the planet Mercury and has a thick nitrogen atmosphere, down to small captured rocks barely a kilometer across. No other planet in the solar system manages gravitational dominance of its local environment quite like Saturn. That gravitational dominance is also a weapon. The region between Jupiter and Saturn forms a gravitational corridor that shapes the orbital paths of objects throughout the solar system. Objects that wander into Saturn's gravitational influence can be slung outward toward the outer solar system, or inward toward the inner planets, toward Earth. This effect has a name. It's called gravitational scattering, and Saturn's mass makes it one of the most efficient gravitational scatterers in the solar system. Here's the counter-evidence that makes this complicated, because honest science demands it. Jupiter is often credited with being Earth's protector, a gravitational broom that sweeps away incoming comets and asteroids, redirecting them away from the inner solar system before they can threaten Earth. There's substantial evidence for this. Jupiter's Great Red Spot is only a few hundred years old, but the planet's impact record is ancient and dense. It has taken hits that Earth would not have survived. But the relationship isn't simple. Some models suggest that Jupiter and Saturn together don't just deflect dangerous objects away from Earth, they actively introduce new ones. The gravitational interplay between the two giant planets can pump asteroids out of the main asteroid belt and redirect them toward the inner solar system on a timescale of millions of years. One dissenting view, published in peer-reviewed planetary science literature, argues that Earth has actually experienced more impacts because of Jupiter and Saturn combined, not fewer. The debate isn't settled. The models disagree on the numbers. What they agree on is this: Saturn's gravity is not passive. It's an active, reshaping force in the architecture of the solar system. Whether it nets out to dangerous or protective depends heavily on which time window you're examining and which objects you're tracking. A scientist named Jonathan Horner at the University of Southern Queensland ran simulations across varying configurations of the solar system, versions with Jupiter but no Saturn, versions with Saturn but no Jupiter, and versions where one or both planets were slightly larger or smaller. The results were jarring. In some configurations, removing Saturn made Earth's impact rate worse. In others, it made it significantly better. The interaction between the two planets is non-linear. It doesn't behave intuitively. Small changes in Saturn's mass or orbital position can produce dramatically different outcomes for the inner solar system over millions of years. That's not reassuring. That's a system that's sensitive in ways we can't fully predict. Now let's talk about Titan, because Titan earns its own beat. Titan is the largest of Saturn's 83 moons. It has a diameter roughly 1.5 times that of our moon. Its atmosphere is denser than Earth's. The surface pressure on Titan is about 1.5 times what you'd feel standing at sea level on Earth. The atmosphere is mostly nitrogen, just like Earth's. But Titan also has rivers, lakes, and seas of liquid methane and ethane, not water, hydrocarbons. It rains methane on Titan. The same substance that burns in your home's gas stove falls from Titan's sky as precipitation and collects in seas hundreds of kilometers across. The Cassini mission found that some of Titan's lakes appeared to have formed by explosive volcanic processes, craters punched into the surface, possibly by ancient eruptions of liquid water or ammonia slush rather than rock. And Titan is drifting away from Saturn faster than any moon in the solar system should drift from its host planet. The expected rate of drift, based on standard tidal models, was 1 centimeter per year. Cassini's precise measurements found Titan drifting at roughly 11 centimeters per year, 11 times faster than the model predicted. That measurement, 11 centimeters per year versus 1 centimeter per year, is the number a scientist described as one of the most unsettling measurements in planetary science. Not because it ends the world, but because it tells us the interior of Saturn is dissipating energy at a rate we didn't account for. The planet's internal processes are more active, more powerful, more dynamic than the standard models suggested. That word standard is doing a lot of work. The standard model was what allowed planetary scientists to feel they understood Saturn reasonably well. Titan's migration rate took that confidence away. If Saturn's tidal dissipation is 11 times stronger than expected, the implications ripple through every calculation involving the planet's moons. Their orbital evolution, their interior heating, their long-term stability. And Enceladus sits in that same tidal environment. The same tidal forces that are accelerating Titan's drift outward are squeezing Enceladus hard enough to maintain a liquid ocean. If those forces are 11 times stronger than the model said, then the energy being dumped into Enceladus is correspondingly more than expected. The ocean beneath the ice might be warmer. The hydrothermal systems might be more active. The plumes might have been running longer. All of that is relevant to the question of whether something lives in that ocean. We haven't looked, not directly. Cassini flew through the plumes and tasted them, but it wasn't equipped for life detection. It wasn't designed for that question. It was designed for a different era of planetary science. When "does it have conditions for life?" was still a preliminary question. We know the answer to that preliminary question now. Enceladus has the conditions. The next mission has to go and ask the harder question directly. NASA has approved a mission called Dragonfly to Titan, a rotorcraft lander scheduled to arrive in 2034. There's also active discussion of an Enceladus orbiter or lander with life detection capability. But no such mission is funded and in development yet. The gap between "we know conditions are right" and "we've gone to check" is roughly 20 years at current planning rates. That gap is a civilizational statement. We found a moon with a subsurface ocean, hydrothermal vents, and organic compounds shooting directly into space, gift-wrapped for investigation. And we're taking 2 decades to plan the follow-up. There's a quieter danger in Saturn's story than the atmospheric winds or the ring dynamics or the tidal forces. It's the danger of understanding something imperfectly and deciding you understand it well enough. The hexagon at the North Pole is still unexplained at a fundamental level. The ring rain is erasing the most recognizable feature of the most recognizable planet in the solar system on a timescale that, cosmically speaking, has already started. Titan's migration rate broke the standard tidal model, and the replacement model hasn't been fully validated. Enceladus is shooting ocean water into space, and we haven't sent a life detector. The gravitational scattering question, whether Saturn protects the inner solar system or endangers it, hasn't been resolved and may require centuries of additional orbital modeling to answer confidently. And the interior of Saturn itself, the metallic hydrogen core, the exact nature of the energy dissipation driving all of these processes, has never been directly sampled. We've never sent a probe deep enough to survive that environment. Everything we know about Saturn's interior is inferred from the outside. Here's what that means in practice. When scientists run models of Saturn's behavior, and those models predict 1 centimeter per year of tidal drift, and the actual measurement comes back 11 centimeters per year, that's not a rounding error. That's the model being wrong by an order of magnitude. In an object as massive and as gravitationally influential as Saturn, being wrong by an order of magnitude has consequences for every downstream calculation, every moon's orbital prediction, every ring stability estimate, every calculation of how long Enceladus has been maintaining its ocean, every guess about whether the conditions for life have been present for 1,000 years or 1 billion years. The number shifted by a factor of 11. The implication shifted by at least as much. And this is why the dangerous label isn't hyperbole. It isn't about atmospheric winds you'll never stand in or lightning bolts in a storm you'll never fly through. It's about a planet so large and so dynamically active that it shapes the fate of objects throughout the solar system, including potentially our own. It's dangerous because we thought we understood it. It's dangerous because it showed us we were wrong by a factor of 11. It's dangerous because beneath one of its 83 moons, in an ocean we've never visited, in water heated by hydrothermal vents whose power we underestimated, something might be swimming, and we haven't gone to check. The hexagon that shouldn't be stable is stable. The rings that look permanent are dissolving. The moon that looked dead is erupting. The tidal model that explained the system was off by a factor of 11. The ocean that has every ingredient for life has never been tested for life. The solar system's most elegant planet turns out to be its most unsettling one. Not because it means us harm, but because every time we got close enough to look carefully, what we found behind the golden rings and the slow, beautiful orbit was something we hadn't predicted, something we couldn't fully explain, something that rewrote the rules. Saturn isn't broken. Our map of it is just catastrophically incomplete. And the universe tends to put its most important secrets inside the things that look, from a distance, the most serene. Thanks for watching, and I'll see you in the next one.